All right, so we're talking about section 5.4. The title of section 5.4 is the fundamental theorem of calculus. And as you know, calculus has a lot of theorems, a whole bunch of theorems. Many of them are named, and many of them are very important, but for a theorem to rise above all the others and be considered the fundamental theorem of calculus, it must be pretty important. And in a moment, we're going to state the fundamental theorem of calculus. But in order to understand it better, I'm going to talk about the difference between indefinite integrals and definite integrals. So the integrals that we did back in section 4.8, those are all indefinite integrals. So I have two integrals here. The integrals that we've already done back in 4.8 that you've practiced, those are called indefinite integrals. And the antiderivative of 2x would be x squared. Right? If we derive x squared, we get 2x. And on the indefinite integrals, you probably know by now that we're supposed to put a plus c, which represents an arbitrary constant. Now, the definite integrals, the great thing is all of the rules that we did back in 4.8, all of the integration rules, they're all hold true for definite integrals. But definite integrals, they have these little numbers on the top and bottom of the integral symbol. You can see the 5 and the 1. But what we do is we still integrate as usual. The integral of 2x is still x squared. But on the definite integrals, we don't put a plus c. We never put plus c. What we do is draw a vertical line back on the end, and then we place the 1 and the 5 on the back like that. And we're going to see what we do with those numbers. So what do those numbers mean? Right, we're going to deal with them right here. So definite integrals are always easily identifiable because they always have numbers on the top and the bottom of the integral symbol, whereas indefinite integrals don't. Indefinite integrals, we always put plus c. Definite integrals, we never put plus c. And again, the great thing is all the integration rules are the same for both types of integrals. But on the definite integrals, once we integrate, we don't put the plus c. It's customary to draw a vertical line, and then you put the numbers on the back like that. At this point, what we do is we plug those numbers in. The top number always goes in first. We always plug the 5 in first. So it'll be 5 squared, and then it's always minus. We always subtract, and then you plug the bottom number in. And this would be 25 minus 1, which is 24. So the answer to that integral is 24. Whenever we do a definite integral, the outcome will always be a numeric answer like that. So whenever we do a definite integral, the answer will be a value, like a number, like 24 or -3 or 0. Now, these numbers, the 1 and the 5, those are called the limits of integration. So let me write that down. Those are referred to as the limits of integration. And once we integrate, we evaluate the answer, x squared, using those numbers, 5 to 1. The way that someone would verbally pronounce this integral, this definite integral, is usually like this. They would say it out loud as the integral of 2x from 1 to 5. That's how you would say it. The 1 is the bottom limit and the 5 is the top limit. After we integrate, we always plug the top number in first, and then we minus, and then we plug the bottom number in. Now, another question you might have is, what in the world does this number on the end mean? What does that 24 mean? It actually means all kinds of things. It depends on what context this integral is in. It depends on what application we're using this integral. One of the applications of definite integrals that we're actually going to see in this section is we can use definite integrals to find the area of a region, and that 24 might represent an area. But there's many more applications of integration. You can use integrals to find the lengths of curves. You can use integrals to find volumes of three-dimensional solids. You can even use definite integrals to help you find the center of mass of, say, a concrete slab or a concrete rod. It helps us to measure fluid dynamics and fluid pressures. You can even use it integrals can be used to to find the surface area of a three-dimensional solid. There's a lot of applications of definite integrals. So what that 24 means, it depends on what context I'm working in. The start of this section is basically just going to have us practice doing definite integrals. And then it gets into area. One of the applications of doing definite integrals is area. We'll do some of those. What I've just done is actually kind of hints at the fundamental theorem of calculus, which I'll now write down on the next slide. Right, so what I'm writing down here is the fundamental theorem of calculus. It says that, so suppose you have a function f of x the fundamental theorem of calculus says the integral of f of x from a to b is equal to big F of b minus big F of a, where big F of x is an antiderivative of little f of x. And the fundamental theorem of calculus is kind of it's kind of straightforward. It's easy to understand. You know, it just says if you integrate little f of x, you basically plug the top number into the answer minus the bottom number. But this has so many applications that it's considered the fundamental theorem of calculus. What I've just written right here, many textbooks, including ours, it actually refers to it as part 2 of the fundamental theorem of calculus. But when many people think of the fundamental theorem of calculus, that's what they think of, this statement right here. So what would part 1 be of the fundamental theorem of calculus? It says something like this. It basically says something like that when you differentiate the integral of a function, you know, it'll just equal f of x. The part 1 is basically saying the integration and the derivative kind of cancel each other out. But the part that we use is this part right here. All right, here we have number 2 in the homework. Again, the nice thing about this section is it's like almost 80–90% the same as the last section. We're just going to integrate, but then at the end, instead of putting a plus c, all you do is plug the numbers in instead. Right? So if you think, so a lot of times the calculus isn't really different in this section than 4.8. It's just the algebra of having to plug numbers in. All right. So first I have to integrate this. So that 4 is a constant. And then when I integrate x cubed, we have to add 1 to the exponent, so it'll be an x to the 4, and then you put a 1 over 4 in the front. And then x cubed over 6, I can write the 1/6 to the side, and when I integrate x cubed, that'll be, I put a 4 up here, and then once again a 1/4. And then we have to evaluate this from 2 to 4. Before I plug the limits in, the 2 and the 4, I'm going to clean this up. So the 4's cancel out, so it looks like we have x to the 4th minus 1 over 24 x to the 4th. And it turns out that these two terms are actually like terms. And if I had thought about it, we actually could have combined them at the very start. Look at that. 4x cubed minus x cubed over 6, those are like terms. We could have combined them at the start instead of integrating them independently. But it doesn't matter. So 1x to the 4th minus 1 over 24x to the 4th, that would be 23 over 24 x to the 4th. Because this 1 in front of the x to the 4th, it's really a 24 over 24. You could look at it that way. So 24 over 24x to the 4th minus 1 over 24x to the 4th is 23x to the 4th. And now we just have to plug in the numbers. So we always plug the top limit in first. So 23 over 24 is a constant. You can leave it factored out. And then when I plug the 4 in, I have 4 to the 4th, and then you always minus. It's always minus. And then you plug the bottom number in. So I left the 23 over 24 factored out. I didn't have to do that. I could have plugged the 4 in and then the 2 in, and that would be the same thing as like distributing the 23 over 24. So now we have 23 over 24, And 4 to the 4th, that's 256. And 2 to the 4th is 16. So we have 23 over 24. 256 minus 16 is 240. But the 24 goes into 24 once, and 24 goes into this 10 times. And 23, so we have 23 times 10, which is 230. And so 230 is the answer here. Now, up here on the right, sometimes I insert the answer that MyMathLab has. And what happened, 230 is the correct answer to this. What happened was I copied in number 2, and then I went back later to get the answer, but MyMathLab had regenerated with different numbers. And so 230 is the correct answer to this one. And the same thing might happen with number 4. You know, I should have put the answers in at the same time I put the question, but on some of these I think I went back and I failed to recall that MyMathLab does regenerate the numbers, obviously. So, all right, so here we're going to integrate this one. So when we integrate, we add 1 to the exponent. So I need to add 1 to negative 8/5. And so 1 is of course the same thing as 5 over 5. So negative 8/5 plus 1 looks like it's negative 3 over 5. And then I have to put a 1 over negative 3 over 5 in the front. And if it were an indefinite integral, I would put plus c, but with the definite integrals, we draw a vertical line and we get ready to plug the numbers in. Before I plug the numbers in, I'm going to clean this up. Instead of 1 over 3/5, you know, that's the same thing as 5/3. And it's much easier to plug numbers in if the exponent on the variable is positive. So I'm going to move the x down. I'm going to move that x down. So it'll be positive 3/5. Now I'm going to plug the numbers in. So we have negative 5 over 3 times 32 to the 3/5 minus negative 5 over 3 times 1 to the 3/5. So we plug the top number in, minus, then we plug the bottom number in. So now I need to figure out what 32 to the 3/5 power is. I'll do that over here. 32 to the 3/5 power. I could put that in radical notation. And the 5th root of 32 is 2, and 2 cubed is 8. So 32 to the 3/5 power is equal to 8. So we have negative 5 over 3 times 8 plus 5 over 1 to the 3/5 power would just be 1. And so we have negative 5 over 24, right? 3 times 8 is 24. And I'm going to turn 5/3 into an equivalent fraction with 24 on the bottom. So I have to multiply 3 by 8 to get 24, so I'll multiply 5 by 8. And so 5/3 is equivalent to 40 over 24. And so the answer is 35 over 24. But that can be reduced. Or maybe it can't, right? 35 over 24. I don't think that, the only factors that go into 35 are 5 and 7, neither of which go into 24, so it can't be reduced, and so that's my answer. All right, number 6. So I have to know the antiderivative of cosecant cotangent. That was back in section 4.8, and the antiderivative of cosecant cotangent is negative cosecant theta, and the 8 just comes out. The 8 is a constant, and the antiderivative of cosecant cotangent is negative cosecant theta. That actually concludes the calculus. Now I have to plug these numbers in, which is going to be the hardest part, is evaluating cosecant at these two numbers. So how about I leave the negative 8 factored out for now? And so I have cosecant of 5 pi over 6 minus cosecant of pi over 6. And to help me out with this, I will draw a triangle. Here's pi over 3, here's pi over 6, 1 square root 3 over 2. Now I need cosecant, so what I could do is remind myself that sine of pi over 6 is 1 over 2, right? Sine is opposite of hypotenuse. So that means cosecant pi over 6 would be 2 over 1, or just 2. And so cosecant pi over 6 is equal to 2. Cosecant 5 pi over 6 would be, here I'll write it out, cosecant 5 pi over 6 would be the same thing as cosecant 1 pi over 6, because that's its reference angle. The only thing is it might potentially be negative. Well, 5 pi over 6 is in quadrant 2, and sine is positive in quadrant 2. So cosecant's positive in quadrant 2 then. So cosecant 5 pi over 6 and cosecant pi over 6 would be the same. And so we have negative 8, cosecant 5 pi over 6 is 2, cosecant pi over 6 is 2, and so it looks like the answer turns out to be 0. And so again, on some of these problems, on all these problems, I attempted to put the answer that my math lab has on the upper right, but on a couple of them, I'm sorry about this, I put the problems in and I was like, well, it might be nice to have the answer that my math lab shows in there too. But then I went back on some of them and I failed to realize that my math lab regenerated the numbers. So I'm sorry, on some of these, the answers I'm getting don't match with my math lab because it's a different problem with different numbers. On number 9 here, it looks like on the right I actually included the actual problem, which I see is the same. So on number 9 I should get this answer because I can see it's the exact same. All right, so here we go. The antiderivative of sine of 2x, whenever you integrate sine, it's going to be a cosine of 2x, but remember from the last section we have to put the 1 over k, right? So the integral of sine kx, you got to put 1 over k. So I need the 1 over 2. Also, I need to recall, do I need a negative or not, right? It can get confusing between deriving and integrating. When you derive sine, the answer is positive cosine, right? But when you integrate sine, I believe we should put a negative, right? Sometimes what I do is when I integrate sine, I know it's going to be cosine. But now thinking about it, if I derive this cosine, do I get back to positive sine over here? And I won't, right? If I derive cosine, it's going to be negative sine. So my answer right here is currently not quite right. It needs to have a negative. And all I got to do now is just plug in the numbers. So whenever we evaluate from limits 0 to pi over 8, the top limit always goes in first. So it's going to be cosine of 2 times pi over 8. But I'm going to take pi over 8 and plug it into that. And I could go ahead and reduce, right? 2 times pi over 8, that's going to be pi over 4. Minus negative 1/2 cosine of 0. And the cosine of pi over 4, right? Cosine pi over 4 is 1 over square root 2. Or if you rationalize that, it'd be square root 2 over 2. And so cosine pi over 4 is square root 2 over 2 plus 1/2. Cosine of 0 is 1. And so we have negative square root 2 over 4 plus 1/2, which I guess I could write as 2 over 4. And, my negative here doesn't really show up, okay? And so, we could now write this as just one quotient, and I'll put the 2 first since it's positive. So we have 2 minus square root 2 over 4. All right, to integrate this, I have to do some algebra first. So we have the integral from -3 to -2. I have to do some algebra first. First, I'm going to split the quotient. I'm going to write y6 over y5 minus 3y cubed over y5. Now that I've split the quotient, I can simplify each of these quotients. y6 divided by y5 would just be y1. And over here, and then when I divide variables, I subtract their exponents, so it'll be y to the negative 2. Now that I've done that algebra, I'm ready to integrate. So the integral of y would be 1/2 y squared. And then I have the negative 3, which I'll just leave to the left for now. Whenever we integrate, we have to add 1 to the exponent. If I add 1 to that negative 2, it would be a negative 1. But then you have to put a 1 over whatever that exponent is in the front of it. And once again, if it were an indefinite integral, we would put plus c, but this is called a definite integral, so I'm going to plug the numbers in a minute. Before we plug the numbers in, though, it's best to clean it up some. So we have 1/2 y squared, and then it looks like I could write plus 3 over y. We have that double negative, so I put a plus, and instead of y negative 1, it's best to move the y down. It'll be easier to plug the numbers in. And so now I'm going to plug the numbers in. First the negative 2, right? We always plug the top limit in first. And so we have 1/2 and then negative 2 squared plus 3 over negative 2 minus, now I'm going to plug the negative 3 in, so I have 1/2 negative 3 squared. And this negative sign right there is going to distribute. That's why I put the brackets here, so it's going to distribute through. And now I put the negative 3 into the second expression. And now I just have a bunch of algebra to do to clean this up. So it looks like I have negative 2 squared is 4. Right, so I have 1/2 of 4, which I guess I could write 2, minus 3/2 minus 9/2. Right, so notice I went ahead and distributed this negative, and then the negative 3 squared I turned into 9, and then 3 over negative 3 here is negative 1, but if I go ahead and distribute the negative, it'd be a positive 1. All right, so now I have just 4 numbers to combine. Maybe what I'll do is I'll add the 2 in the front and the 1 on the back, so that's 3. And negative 3/2 minus 9/2 is negative 12/2, right? Negative 3/2 minus 9/2, yep, that's negative 12/2. So I have 3 minus 6, which is negative 3. Okay, here's another example. So we have to integrate 6 over x. Let's look at that maybe off to the side right here. The integral of 6 over x, the first thing you could do is pull that 6 out since it's a constant. And the antiderivative of 1 over x, recall from section 4.8, is natural log absolute value of x. Now, we're about to plug in the numbers 1 to 5, though, which are positive. So you could leave off the absolute value bars because we're going to plug in positive numbers. So the integral of 6 over x is 6 natural log x. And then the integral of e to the negative x, whenever you integrate e to the negative x, or e to the kx, it'll be e to the kx, so it is e to the negative x, but I have to put that 1 over k in the front, and k is negative 1. Now we just have to evaluate this. Before I evaluate it, I'll clean it up. I have a double negative, and instead of e to the negative x, I'm going to move that e down, that way the exponent's positive. And then we plug the top number in first, so we have 6 natural log 5 plus 1 over e to the 5 minus, and then we plug the 1 in. 6 natural log 1 plus 1 over e to the 1. Now, natural log 1 is just 0, right? Natural log of 1 is equal to 0, so this goes away. And so we have 6 natural log 5 plus 1 over e to the 5 minus 1 over e. And there's nothing more I can do to simplify that. So that's what you would type into MyMathLab. All right, so we've been doing some definite integrals. Now we're going to actually see an application of definite integrals, and that's using integration to find area. I'm going to do an example first, and then I'll draw like a generic picture illustrating a generic guideline. Right, so let's pretend we have the function. I'm going to make up a linear function so it's easier. How about f of x equals 2x plus 1? So that's a linear function. I'm going to graph it. So let's see, 1, 2. I'm making a coordinate plane. Notice if x is equal to 0, then y would be 1. If I plug 1 in for x, I think I get 3. And if I plug, say, 4 in for x, that'd be 9. So if x is equal to 4, it looks like f of 4 is 9 up here. And so this right here, this green line, it's the graph of f of x. And let's pretend that I wanted to find the area. Let's pretend I wanted to find the area between 1 and 4. Right. So what I'm going to try to do is find this area that I'm shading in red. All right. So let's pretend that my goal is to find this area in red. Now, that area right there is actually enclosed by a four-sided figure. It's a quadrilateral, and it happens to be a trapezoid. And so there's actually a formula for finding the area of a trapezoid. If a trapezoid is a four-sided figure that has one pair of parallel sides, and this is the height, and then these are called the bases. The parallel sides are called the bases. And the area of a trapezoid can be found by taking half its height and then multiplying that by the sum of the bases. So I can actually find the area of this figure in this area in red by using that geometrical formula, which I'm going to do. The height is the distance that connects the two bases. So this trapezoid is actually flipped upside down, up on its side or something like that. The area is 3. The height is 3, right? This is the height right here that connects the two parallel sides. So half of the height, and then this is one base. That length is 3, and then this length over here is 9. Right? So the bases are the parallel sides. That's 3 and 9. And so that's 3 halves times 12, which is 18. And so 18 square units is that area in red. I didn't need calculus for that. But check this stuff out right here. Watch what happens when I integrate the function. If I just integrate the function from 1 to 4. The antiderivative of 2x is x squared, and the antiderivative of the 1 is x. And then we plug the top number in. If I plug 4 in for the x's, it looks like I'll get 16 plus 4 minus, and then now you plug the 1's in, which will just be 1 plus 1. And so that's 20 minus the 2 and 18. So look at this out. We get the same answer. So what I'm attempting to show is that one application of computing definite integrals is it can help us to find the area of a region. Now, when you have a linear function, maybe we don't need calculus because we can use geometry. But imagine if we wanted to do this. What if our function was like this? And we wanted to find the area from, say, A to B. Right? There's no geometrical formula for that anymore. But guess what? Calculus doesn't care. All we would do is integrate g of x from a to b, and we would get the area. So calculus allows us to find areas of shapes or regions that geometry can't do. right? Calculus will allow us to find area of irregular shapes, which is very beautiful. Like what if I wanted to find the area of a lake or something like that, right? It doesn't follow an exact shape. And calculus 2 will actually extend this and see that we can use integration to find volume of three-dimensional solids that I couldn't normally do with geometry. And what I'm going to do here is draw some like generic guidelines. So here's a coordinate plane. Let's say we had a function like this in green, and I'll call that f of x. And here's x equals a, here's x equals b. And so let's suppose I wanted to find this area in red. And so that area in red I will call capital A. That area can be found by integrating the function from one end to the other, right? So that's exactly what we just saw. All right. Well, now let's look at another picture though. What if I have a function that maybe does something like this? You know, it goes on both sides of the x-axis. Maybe I'll call this function, I'll give it a different name. I'll call it g of x. Let's pretend that maybe I wanted, how about we call that a, I'll call this b, and I'll call this x-coordinate c. And I'm going to color in this region, and I'll color in this region, and maybe I'll refer to that region as a sub 2, and I'll call that region a sub 1. Right, well, if I wanted to find a sub 2, that's no different than the picture on the top. To get a sub 2, I would just integrate g of x from b to c. Okay, that's no different than the first picture. But notice a sub 1 is below the x-axis, isn't it? If I were to integrate, whenever you integrate a function and it's completely below the x-axis over a region of the domain, the answer will come out negative. I propose that if you integrate g of x from a to b, the answer will come out negative. And the reason why I know that is because it's below the x-axis completely. And area is always positive. So we would have to absolute value this. We'd have to absolute value that to get the area. We're going to do some examples in a moment where they're going to say find all the area between a function and the x-axis over a region. And it turns out that what we have to do first is identify x-intercepts. Now, notice that a and b are x-intercepts. In order to properly identify the area between a function and the x-axis, we need the x-intercepts because we need to know where to break up the integral at. And we'll do an example like that in a moment. And that's actually right here. I think this is the last one in the video. All right, it says find the total area between the region between the x-axis and the graph of this function right here. All right, so the first thing I need to do is find x-intercepts. All right, see, the reason why we need x-intercepts is because well, let's look at this example right here for a moment. Let's say the function was just y equals x cubed. Right, if I watch what happens if I integrate x cubed from, say, negative 2 to 2. The integral of x cubed is 1/4 x to the 4th. And if I plug a 2 into 1/4 x to the 4th, I'll get 4. It'll be a 4th of 16, so I'll get 4 minus. But guess what? If I plug negative 2 into this, I'll get the same answer as if I plug 2 in, and the answer is 0. But if we were to graph y equals x cubed between negative 2 and 2, it would look like this. And obviously the area between the function and the x-axis is not 0. But what's happening is when I evaluate the integral from negative 2 to 2, the area of that region right there on the right is 4, and the area of this region is also 4, but the integral is computing it as negative 4. right? And it's canceling out the two answers, giving me 0, giving me the incorrect answer. So if you integrate x cubed from -2 to 2, the correct answer is 0. But when we use integration as a tool to find area, we have to use it correctly. The tool will only work if I use it the right way, right? And so when I use integration as a tool to get area, anytime that I integrate a function below the x-axis, it's going to come out negative, and it should. That's the way it is. But I have to recall the absolute value of that section. So we have to identify any x-intercepts and break up the integral and integrate independently between the different regions. So let's see. So the first thing I'm going to do is find x-intercepts. To find x-intercepts, what we do is we plug a 0 in for y and then solve for x. Okay, so it looks like I'm going to solve by factoring. I can factor in x out. And then I can factor the trinomial as x plus 3, x plus 1. And so I get 3 answers. X equals 0, x equals -3, and x equals -1. Right? To successfully do number 16, you don't need to graph anything, but I'm going to do a little graph to kind of help understand what's going on. Right, so it's a cubic function, and we just found out that we have x-intercepts at 0, -3, and -1. So at -3, there's an x-intercept. At 0, there's an x-intercept. And at -1, there's an x-intercept. So the graph of this function is going to go like this. It's going to go whoop, whoop. So what you see in green, that's the graph of this function. And they want me to find the area of the region between this function and the x-axis. So there's actually two areas. There's two regions. I got to find this area right here, right? That area is enclosed between the function and x-axis, and this area right here. If you want to, you can give those areas names. You can call that maybe A1, and maybe I'll call that one A2. And what we have to do is integrate both of those individually. To get A1, I will integrate from -3 to -1. And to get A2, I'll integrate from -1 to 0. But do you see how A2 is below the x-axis? So after I evaluate the integral of A2, it's guaranteed to be negative. If I evaluate the integral to get A2 and it doesn't come out negative, that means I've done something wrong because it's below the x-axis. But what I'll do is I'll absolute value that answer. I'll make it positive. And then once I get A2 and I get A1, I'll add them together, and that'll be the total area. All right, so I have another slide. I'm gonna pause the video and go to the next slide. I have to pause it so I can copy down this function because I have to integrate that. All right, so to get A1, we have to integrate the function, which was x cubed plus 4x squared plus 3x, from -3 to -1. And A1 is is above the x-axis, so this definitely should be positive. So integral of x cubed, that'd be 1/4 x to the 4th. The antiderivative of 4x squared would be 4/3 x cubed, and 3x would be 3/2 x squared. Now I have to plug these numbers in. So here we go. If we put the -1 into x to the 4th, that would just, here, I'll write it out just in case somebody wants. So we have 1/4 -1 to the 4th plus 4/3 -1 cubed plus 3/2 -1 squared, and then minus, now we put the -3 in. It's a lot of work plugging all these numbers in. All right, so now we have 1/4 minus 4/3 plus 3/2. And then I'm going to distribute that negative. So minus 3 to the 4th is 81. So that'd be 81/4. Then it's going to be a plus because negative 3 cubed is negative, but this negative I'm distributing. And so that'll be negative 3 cubed is negative 27. But I can reduce it. I can reduce that 27 with this 3, making it back to a negative 9. And negative 9 times 4, that'll be a 36. I'm going to do that again just to make sure, right? So negative 3 cubed is negative 27. Divided by 3 is negative 9. Times the 4, negative 36. But then this negative I'm distributing, so positive 36. Minus, and then 3/2 times 9, that's 27/2. Yep, negative 3 squared is 9 times 3. Yep. Okay. Now I have a bunch of numbers, a lot of fractions and stuff to combine here. So the 1/4 minus 81/4, that would be negative 80/4. Right, so what I just did, I combined 1/4 minus this 81, that'd be negative 80/4. And then I have, I guess I'll go ahead and try to combine these two. Oops, I saw the negative 27/2 on the end. Maybe I'll do that one. So I'll just rewrite the negative 4/3. So the 3/2 and the negative 27/2 would make negative 24/2. And then I have the plus 36. And continuing on here, negative 80 divided by 4 is negative 20 minus the 4/3. And then negative 24/2, that's negative 12 plus the 36. Now I'm going to combine the integers. Negative 20 minus 12 is negative 32 plus the 36 is 4 minus 4/3. And so that's 12/3 minus 4/3. And so 8/3 is what I got for A1. Now I still got to do A2, but we don't need to integrate again, right? We already integrated once, and so there's no need to do it again. So we already integrated, and we got 1/4 x to the 4th plus 4/3 x cubed plus 3/2 x squared. But now we need to evaluate this from -1 to 0. If you remember from the last slide on this sketch, we're integrating from -1 to 0 to get A2. And this should be a negative answer. The nice thing is, 0 is one of the best limits to have. If I plug a 0 into this trinomial into the x's, it's just going to be a big 0, right? Because 0 to the 4th is 0, 0 cubed. So 0 is great. Minus, now I have to plug -1 into all this. But we actually already did plug -1 into all this. It came out to this stuff back up here. Actually just this stuff, and not the 81/4 came from the other side. So if I plug a -1 in, once again we're going to get 1/4, and then if I plug a -1, then it'll be a negative 4/3 plus the 3/2. It's the same stuff that we got right up here. And so now I need to evaluate this, and so I'm going to get some common denominators, I guess. Looks like it'd be 12. So the -1/4, maybe I'll write that as negative 3/12 plus 4/3 would be 16/12. And then 3/2, that would be negative 18/12. And so what do all those three numbers add up to? Negative 5/12, I think. Let me do that. So negative 3 plus 16 is 13. Yep, negative 5/12. And notice it came out negative like it should have been because it was below the x-axis. So the area of A2 region would be positive 5/12. All right, so the goal was to find the total area. The total area is A1 plus A2. right? But I have to, but A2 needs to be absolute value because it's negative. So the total area is the sum of the two regions. So the area of the first region is 8/3, and the area of the next region would be 5/12. I have to absolute value the negative 5/12. And so let's get a common denominator just to add these two. So 5/12 is good. And 8/3, I have to multiply 3 by 4 to make it a 12. So that means I got to multiply the 8 by 4, which would be 32. And so it looks like the answer is 37/12. 37/12 is the total area of between that function and the x-axis.